Hello everyone, and welcome to this virtual lecture course on Quantum Condensed Matter Physics. I'm Dr. Andrew Mitchell, and in this lecture we'll be discussing the equations of motion method for Green's functions in quantum many-body systems involving fermions. In the recent lectures, we've been developing the Green's function formalism. We saw how Green's functions correspond to electron propagators. They tell us about the dynamics of electrons in materials. We used the machinery of statistical mechanics to do the brute force calculation of some of these Green's functions for simple systems. In particular, we derived the Green's function for an electron gas, and then we were able to relate this to the class of non-interacting quadratic tight-binding models. We developed a matrix mechanics of Green's functions, and we saw the utility of this with several examples. In this lecture, we're going to talk about the equations of motion method, which is a complementary technique. In the first part, we will derive the equations of motion, and then in the second part, we'll be applying this to lots of interesting and instructive examples. We'll talk about quadratic, non-interacting tight-binding models, and we'll see how equations of motion lead to a set of equations which can then be solved to obtain Green's functions in closed form. The equations of motion method really simplifies these problems and makes light work of difficult problems. We'll talk about simple systems involving a few orbitals, as well as macroscopic systems involving 10 to the 23 orbitals. In the last part of the lecture, we're going to talk about the concept of electron scattering and quantum impurity problems. We'll talk about the T-matrix equation, which allows us to relate the scattering of electrons when one introduces a defect or an impurity into the system. And we'll also talk about the resonant level model, and how, if you introduce an impurity into a system, how this changes the properties of the system, and how we can relate the Green's function of the impurity to the Green's function of the environment. This is a really nice technique. It's a workhorse of quantum many-body physics, and this will be the topic of today's lecture. So let's get down to work.
So in this lecture, we'll be discussing the equations of motion technique for Green's functions. The equations of motion methodology is really powerful and useful for understanding the dynamics of quantum many-particle systems. The method allows to relate certain Green's functions to other Green's functions, and for non-interacting systems, the system of equations that we obtain using equations of motion closes, and we can find exact analytic solutions for the Green's functions. In this lecture, I'll first derive the equations of motion, and then I'll apply them to get useful results for several important systems. In this lecture, I'll mainly be focusing on single-particle Green's functions for fermionic systems. However, the equations of motion technique can also be generalized to higher-order Green's functions for fermionic or bosonic systems. Also, I'll only consider in this lecture the retarded Green's functions for systems in equilibrium. We start from the definition of the retarded double-time single-particle propagator. This is given in terms of the thermal expectation value of these time-dependent operators. The curly brackets here, as usual, denote the anti-commutator, and the theta function is the Heaviside step function. This Green's function is telling us about the probability that if we put a particle into our many-body system at orbital B at time t primed, then we can take it out again in orbital A at a later time t. We now simply take the time derivative of this expression. Specifically, we're going to take I times the partial derivative of d by dt of this Green's function. Notice that this partial derivative will only act on the t rather than the t-primed variable. Our Green's function involves two factors that depend on the variable t. First of all, we have this theta function, theta of t minus t-primed, and secondly, we have the actual correlation function itself, which involves this operator Ca evaluated at time t. Therefore, on the right-hand side, we need to apply product rule to calculate these partial derivatives. In the first term, I've emphasized here in blue that I'm taking the derivative of the Heaviside step function, whilst leaving alone the correlation function, whereas in the second term, I'm leaving the step function alone while taking the time derivative of the Ca of t operator. I can now recognize that the derivative of the step function is equal to the delta function, and also here I'm taking the time derivative of an operator which I can express in terms of the commutator of that operator with the Hamiltonian. And the result of this whole commutator is then evaluated at time t. And as usual, I'm setting h bar to 1 in all of these calculations. So we then use these relations to write the following. And this is basically the equation of motion that we're after. If we take the time derivative of a particular Green's function, then we end up with this static piece here. This results because the time derivative of the step function is the delta function, which basically sets t is equal to t primed in this expression. Therefore, we have the thermal expectation value of the anti-commutator of two operators evaluated at the same instant in time. Now, if we're talking about an equilibrium system with a Hamiltonian that doesn't depend on time, then that means we'll have time translation invariance of these kind of objects. We might as well then evaluate this at t equals 0, which is what I've written explicitly here. It ends up just being some thermal expectation value of an operator. Which operator? Well, it's just the anti-commutator of these two operators. In the case of fermionic operators, we know that the anti-commutator of Ca and Cb dagger is of course delta Ab, and the expectation value of delta Ab is just delta Ab, it's a constant. What about this second term? Well, we see immediately that this is just another kind of Green's function. Our original Green's function, Gab of t and t primed, was defined in this way. You can see that this correlation function here is closely related, except instead of Ca evaluated at time t, we have the commutator, this time, of the Hamiltonian with Ca evaluated at time t. So it's not the same Green's function that appears on the left, it's a different one. It involves a different operator here. Typically, we'll be working in the frequency domain rather than the time domain. So we can Fourier transform, or actually Laplace transform, these Green's functions. In fact, we can take the Laplace transform of this entire equation of motion. So let's see what we get when we do that. We therefore obtain the following. We integrate over the time difference t minus t primed, which we can do in this system because of the time translation invariance. We recognize that the Green's functions as a function of t and t primed actually only depend on the collective variable t minus t primed. And then we integrate from 0 to infinity of the Laplace transformation kernel e to the iz t minus t primed in this case. And then we have I d by dt of the Green's function on the left. On the right hand side, we perform the same Laplace transformation. This Kronecker delta here survives that integral. We simply get delta AB as a constant term, plus the Laplace transformation of this correlation function. So the second term here is simply the retarded Green's function in terms of the complex frequency z. This first term is a little harder because we have this additional time derivative in here. However, we can treat that simply by integrating by parts here. When we do the integration by parts, and noting the limits of the integration are from 0 to infinity, and noting that z has a positive infinitesimal imaginary part, then we simply obtain that this is equal to z times the Laplace transformation of Gab. So we've related one frequency domain Green's function to another. Writing this in the so-called Zuberev notation, we have something that looks very simple indeed. On the left-hand side, I have the complex variable z multiplied by a Green's function involving operators Ca and Cb dagger. On the right-hand side, I have the Kronecker delta, delta Ab. So this is equal to 0 if these are different orbitals, and it's equal to 1 if Ca and Cb refer to the same orbital. Then we have another correlation function. This is not the same as the one on the left-hand side, generically, because we have different operators. Here, the Green's function involves the operator which is formed by the commutator of Ca with the Hamiltonian. And then after the semicolon here, we have Cb dagger as before. The equation of motion that I've derived here was obtained by taking the partial derivative d by dt of our original Green's function. However, we could have also taken the partial derivative of t primed. That would then affect this second operator here, which in the time domain carries the argument t primed. Working through all the steps as before, we now obtain a different equation of motion, where this time it's the operator CB dagger that gets replaced by the commutator of the Hamiltonian and CB dagger. In both equations, however, we see that we relate a given Green's function to some other Green's function. Which Green's function sits on the right-hand side here, of course, depends on the Hamiltonian. We'll do plenty of examples later in this lecture. We can also generalize this to Green's functions involving arbitrary operators A and B. We'll see that this will be useful when we consider later on interacting problems and also quantum transport using the Kubo formula. But for now, I'll just write down these generalized equations of motion, in which on the left-hand side we have the complex variable z multiplied by this generalized Green's function formed by operators A and B. And then on the right-hand side, we have some static expectation value of the operators formed by either the anti-commutator or the commutator of A and B, depending on whether A and B are fermionic or bosonic operators. If A and B are fermionic operators, for example, these creation and annihilation operators up here, then we have the usual anti-commutator, which corresponds to fermions. If A and B are bosonic, then we have the commutator here. That's what this plus and minus means. Then we add to this static term a dynamical term, which is another Green's function, formed by the commutator of A with the Hamiltonian, or with the Hamiltonian and B. We have a choice of which one to use here. Notice, however, that in this second term, in both equations, we always have the commutator. This doesn't depend on whether we have fermionic or bosonic operators. This is always the commutator and never the anti-commutator. And that's because this term is arising from the time derivative of the operator, which from the Heisenberg relation involves the commutator with the Hamiltonian. So we'll come back to explicit examples of using these generalized forms later on. But for the rest of this lecture, we're going to stick with the simplified version, which we obtain when A and B are not only fermionic operators, but they're specifically the annihilation operators and the creation operators. So let's now have a look at the equations of motion in action through some simple but instructive examples. The first of which is our favourite example of the single quantum orbital. The Hamiltonian is written down here. It's simply the level energy epsilon times the number operator for that orbital. There's only one Green's function we can write down for this system, which I'll call g of z. In the Zubrev notation, it's simply c with c dagger. In the lecture where I introduced the definitions of the Green's functions, we calculated this object explicitly using the fundamental definitions from statistical mechanics of the thermal expectation values of time-dependent operators. Here we'll obtain the same result using equations of motion, and we'll see that is extremely straightforward indeed. The equation of motion is as follows. It's z times the Green's function is equal to 1 plus this new correlation function. This 1 here is coming from the Kronecker delta, and that's arising because I'm working out the expectation value of the anti-commutator of the two operators, which is of course, in this case, simply 1. To understand the meaning of this second correlation function here, we have to compute explicitly the commutator of the Hamiltonian with this operator, in this case simply c dagger. Just substituting in the Hamiltonian into this expression, we get the following. But notice here that epsilon is of course just the coupling constant in this Hamiltonian. It's just a number, and so it commutes through these operators. In that case, we can see from the second term that we have two c daggers in a row, and that will give us 0, because we can't create a particle into an orbital and then create another one because of the Pauli principle. On the other hand, in this first term, we create an electron, destroy it, and create it. And so overall, that's equivalent to just simply creating an electron. So this commutator is actually equal to epsilon c dagger. We can also obtain the same result simply by using the properties of the anti-commutators for fermions and rearranging these expressions here. I'll do some examples of that later. So plugging that in, we obtain the following expression, which is rather straightforward. Notice also that the same object appears on the left and the right. This we defined as our Green's function g of z, and therefore so is this. We can then collect the factors of g of z on the left-hand side and rearrange to give us our final result, which is that g of z is simply 1 over z minus epsilon. And this is the result that we found previously, actually via quite a bit of hard work. Here it just pops out automatically and very nicely using the equations of motion technique. The spectral function a of omega, defined as minus 1 upon pi of the imaginary part of g retarded, where we take the analytic continuation to the real axis, simply gives us our delta function. Sketching the spectral function a of omega versus the frequency omega simply gives us a delta function located at the level energy epsilon. The next important example is that of the electron gas. It's a quadratic or non-interacting Hamiltonian in the diagonal representation, where I have a many-body system, where here we could really have 10 to the 23 or an infinite number of electrons in the system, and we sum over these quantum orbitals, each of which has an energy epsilon k that depends on which orbital we're talking about. So we have these ck operators, and for each orbital labelled k, we have a specific epsilon k. How the energy epsilon k depends on k is referred to as the dispersion relation. Now, the importance of this Hamiltonian is not really that it represents a specific important physical system, but rather that any non-interacting or quadratic Hamiltonian can be cast into this form by diagonalizing the Hamiltonian operator through a canonical transformation of our fermionic creation annihilation operators, as discussed in the previous lectures at length. In turn, this means that we can relate the Green's functions of any system that we're interested in, so long as it's such a non-interacting quadratic Hamiltonian, in terms of the Green's functions of this system. And that was the focus of the previous lecture. So let's go ahead and apply the equations of motion to this system. We can define different Green's functions for this system, which I'll label g kk primed of z. In Zubarev notation, they'll be formed from the retarded correlator of the operator ck with ck primed dagger. Previously, we showed that these are diagonal in k and k primed, so let's see how that property emerges using equations of motion. The equation of motion takes this form, where I have the complex variable z multiplied by this Green's function is equal to the Kronecker delta of kk primed plus this new Green's function. To understand this object, we need to evaluate this commutator. We can write that commutator out in the following form. Here we actually have to be a little bit careful, because the Hamiltonian operator here involves a sum over k. However, we cannot use k or k primed as our index for this sum, because they're already being in use in the definition of our Green's function. So therefore I need to pick a different dummy variable over which I sum in the Hamiltonian, and I've decided to call that k double primed. So everywhere in my Hamiltonian operator I'm using now, instead of k, I'm using the label k double primed. As I said, that's simply because k and k primed are already being used. So here I have a sum over k double primed, and then I'm evaluating the commutator of that object with an operator c k primed, and this is a specific k primed. This is not being summed over. Okay, so now we have to be a little more careful to evaluate this commutator. The way we'll do that is to use the fundamental anti-commutation relations for fermions to help us out. So let me explain the general strategy to work out these kind of commutators. We have two different terms here. The strategy in general is to make one of the two terms, for example this second one here, look like the first term. To do that, we need to take this c k primed dagger operator and move it through all of these other operators to the end. That's what appears in this first term. However, moving this operator through these other operators will invoke the anti-commutation relations as we reorder those operators. So let's just see that in practice. First of all, notice that ck primed dagger commutes with the sum and also with this constant epsilon k double primed here, but it does not in general commute with other operators, for example these fermionic operators here. So let's remind ourselves of the fundamental Pheromonic anti-commutation relations, which are that the anti-commutator Ca with Cb dagger is equal to the Kronecker delta, whereas if I have two daggers, then this is always equal to 0, independently of which orbitals we're talking about. This second property tells us that if we swap the order of two creation operators, then we just get this extra minus sign here. And this is exactly what we have in this situation. So I will take this operator Ck primed dagger, and I want to swap the order with the Ck double primed dagger. And when I do that, I'm going to get this minus sign. When I do that, in the second term, I will now get plus the sum over k double primed of epsilon k double primed times the creation operator Ck double primed dagger times now Ck primed dagger Ck double primed. To turn this second term into something that looks like the first term, we're not yet finished. We need to additionally hop this operator over the last one. And in this case, we're going to have to utilize this first anti-commutation relation that I've written down here, because we see that we have one creation operator and one annihilation operator. When I insert this anti-commutator into this expression here for swapping the order of these two operators, I see that I get this factor of the Kronecker delta. This then gives me the sum over two terms. First of all, I have plus the sum over k double primed of epsilon k double primed times the creation operator Ck double primed dagger, and then minus Ck double primed Ck primed dagger. Now this term, with this minus sign, exactly cancels with our first term in the commutator. And in fact, that was the whole reason for reordering these terms, so that we can actually compare this first term with the second term. But we also see this piece with the Kronecker delta. There we have the sum over k double primed, epsilon k double primed, times the creation operator Ck double primed dagger times this Kronecker delta. And this Kronecker delta collapses this sum over k double primed to the single term where k double primed is equal to k primed. In which case, we can write overall that the commutator of the Hamiltonian with Ck primed dagger is simply epsilon k primed Ck primed dagger. I recommend that you work through these steps yourself and confirm this result. So returning to the equations of motion, I can plug this in, and I see that I have the same Green's function on the left and the right, just as before. But notice here, unlike the equation of motion for a single orbital, now we have this Kronecker delta, delta kk primed, and the energy of this orbital is epsilon k primed, corresponding to this second operator here. Recognizing this Green's function as our definition of g kk primed of z, I then can rearrange this equation to find the following closed form for the Green's function. We see that it's equal to delta kk primed over z minus epsilon k primed. So indeed, we see that these Green's functions are diagonal in k-space. Also, we can write this in a slightly different way, because we see that this Green's function is only finite if k is equal to k primed, and therefore downstairs we have this epsilon k primed. We can also write that simply in terms of epsilon k. That follows simply from the fact that epsilon k is equal to epsilon k primed if k is equal to k primed. As I explained at length in the previous lecture, once you know the general result for Green's functions of the non-interacting electron gas, we can write down the Green's functions for any quadratic non-interacting system simply by diagonalizing the Hamiltonian, and then casting the real space Green's functions in terms of the Green's functions of our diagonal bases. For example, if we have a translationally invariant or periodic system, then we can relate our real space Green's functions to our momentum space Green's functions. The momentum space Green's functions are diagonal in k-space, and they're also trivial if you know what the dispersion relation is. However, one of the great advantages of the equations of motion technique is that we can apply them directly in real space without having to go through the diagonal representation. This can be highly advantageous because it means that we don't have to actually diagonalize our system. we can then totally avoid the process of finding the unitary matrix which performs the canonical transformation to the diagonal bases. So let's do a simple example of that. Consider here the tight binding dimer. As a cartoon, one can imagine two quantum orbitals connected by some tunneling matrix element T. Here I'm imagining that T can be complex, meaning that if the Hamiltonian is Hermitian, which it must be, meaning H is equal to H dagger, then this first term for the forward process is parameterized by T. Then we must have the complex conjugate, T star, for this backwards process. Now, instead of diagonalizing this Hamiltonian, let's just take it in real space and work out the Green's functions directly using the equations of motion method. The Green's functions I'll be interested in will be of this type, Gij of z, which are formed by the operators Ci and Cj dagger, where I and j are 1 and 2 in this case. The equation of motion for orbital 1 is z g11 of z is equal to 1, plus another Green's function involving this operator formed by the commutator of the Hamiltonian with C1 dagger. We can expand the commutator using the explicit definition of our Hamiltonian as follows. And now we apply the same strategy as before. We wish to reorder the operators in this second term to get them to look like the operators in the first term. And the way we do that is by hopping this operator C1 dagger all the way onto the right-hand side. Applying the same logic as before, we can see that C1 dagger will give us 0, so this first term will be 0. And actually, we can apply that same logic to the first term over here, because again, I will have C1 dagger, and by the Pauli principle, that always gives 0. When we swap the order of C1 dagger and C2 dagger, we'll incur a minus sign. Then we obtain the following terms. But we're not quite done. To be able to compare these two, I still need to hop this orbital C1 dagger over here. Then I can compare these two terms. Using the anti-commutator for C1 and C1 dagger, I can then write it in the following way. And we immediately see that this first term here cancels with this second part, leaving us overall simply with T star C2 dagger. Plugging this back into the equation of motion, we find that Z times G11 is equal to 1 plus T star of this correlation function formed by the operators C1 and C2 dagger. But of course, this latter object is simply the Green's function G12 of Z. So we see that we have related G11 to G12. But this is not quite what we want. We would like to be able to find an explicit expression for G11 and G12 and so on. And in fact, we can do that simply by applying the equations of motion a second time, this time not for G11, but for the Green's function G12 that appears on the right-hand side here. The equation of motion then is Z times G12 is equal to 0 this time, because we're looking at different operators, 1 and 2, and then the correlation function formed by the operator C1 and the operator formed by the commutator of the Hamiltonian with C2 dagger. I will leave it as an exercise for you to confirm that this commutator evaluates to T times C1 dagger. And therefore, on the right-hand side of this equation, I find simply T times G11 of Z. This is nice because the system of equations has closed. If I substitute in our expression for G12 into our first expression, I can then eliminate G12 and write everything in terms of G11. Then I get that Z times G11 is equal to 1 plus T star times T over Z of G11 of Z again. I can now solve this equation for G11, and I also notice that T star is simply the square modulus of T. I find that G11 of Z is equal to 1 over Z minus the square modulus of T over Z. Furthermore, I can extract G12 of Z because I know that that's simply equal to G11 of Z times T over Z, and I've just found G11. So with 2 steps of our equations of motion, we can find all of these Green's functions, G11 as well as G12. In fact, we could also obtain G22 in a similar fashion. In this particular case, there is a symmetry between 1 and 2, so G22 actually has exactly the same form. Try that yourselves. So we have a Green's function that looks like this. What does the corresponding spectral function look like? As usual, we can write the local spectral function for orbital number 1 in terms of the retarded Green's function for orbital 1. So the spectral function immediately follows from our explicit expression for this Green's function. Multiplying by z, top and bottom, and then using the difference of 2 squares gives us the following. We can now do partial fractions upon this to obtain the Green's function as a sum of 2 poles. The final result immediately follows. We see that we have 1/2 of z plus t plus 1/2 of z minus t. We can therefore write the local spectral function a1 of omega as a half times the delta function omega plus modulus of t plus another delta function which also has a weight of 1/2 delta of omega minus t. So we see that the spectral function for orbital 1 of this system involves 2 delta peaks, one at minus t and one at plus t. Both of these delta peaks are of weight 1/2, such that the total integral of the spectral function is equal to 1. The spectrum is of course always properly normalized, and that's a good sanity check that is satisfied in this case. So to emphasize once again, the nice thing about these equations of motion is not only that it's a rather simple and straightforward method, but also that we don't have to actually diagonalize the Hamiltonian. We obtained this Green's function simply by solving these coupled equations of motion. The next example is that of a semi-infinite type-binding chain. We've encountered this example a few times already, but here I'm introducing some additional complexities to illustrate the power of the equations of motion technique. So the setup is illustrated here. I imagine that I have a semi-infinite chain, which means that I start with orbital 1, then it goes to orbital 2, and so on, all the way up to infinity. I imagine now, however, that I have different tunneling matrix elements between each pair of sites, T1, T2, T3, and so on, and these can be different from each other. I'll also introduce potential energies, these level energies for each orbital, epsilon 1, epsilon 2, and so on for each orbital, and again, in general, they can be different. So let's look at the Green's function at the end of this chain. This is G11. As we'll see, the equations of motion technique will generate some other kinds of Green's function. So let's be more general in our definition and write that Gij in Zubrev notation is simply this usual object involving Ci and Cj dagger. The equation of motion for G11 is the following. And I'll leave it as an exercise for you to confirm that the commutator of H with C1 dagger is epsilon 1 C1 dagger plus T1 star C2 dagger. Plugging that in and utilizing this definition of our Green's functions, we simply see that Zg11 is equal to 1 plus epsilon 1 G11 back again, plus T1 star times G12 of Z. So the equations have not yet closed. We've related the G11 Green's function to a different Green's function, G12. So in an exactly analogous fashion to on the previous slide, with the previous example of the type-binding dimer, here we see that the approach will be to do equations of motion a second time, but now for this unknown correlator, G12. We write that Zg12 is equal to 0 plus this new correlation function, where now we need to calculate the commutator of the Hamiltonian with the operator C2 dagger. In this case, we get 3 terms. And again, I will leave it as an exercise for you to confirm this result. Therefore, we have an equation of motion for G12 that involves G12 back again, also G11, but now we've proliferated further down the chain and we obtain a new Green's function, G13. So this is a new term that we did not encounter in the case of the type-binding dimer, which only consisted of 2 sides. In the chain geometry, we get this extra term, and the equations still have not closed. In fact, it's very straightforward to generalize this result to the Green's function G1n for any n greater than 1. and we'll be using this result to solve recursively our equations of motion for G11. If you like, you can stop the video now and have a play with this yourself and see if you can find that solution. Otherwise, I will tell you the trick to it. It's not completely obvious how you can use this information to find a closed form expression for the Green's function G11, but there is a trick, so let me tell you that now. So to summarize, we have two basic equations. One is for the Green's function at the end of the chain, G11, and that's a little bit special. And then in general, for any other n greater than 1, we can write down an equation of motion for G1n. In the latter, we see that G1n is related on the chain to the Green's function before, this is Gn minus 1, and the Green's function after, G1n plus 1. So let's label the first equation, equation 1, and the second, equation 2. From equation 1, I can rearrange this slightly to give me an expression for G11, which will take the following form. 1 over z minus epsilon 1 minus T1 star G12 of z over G11 of z. So this might seem like a little strange way of writing it. All I'm doing is multiplying top and bottom on this term by G11 of z, bringing it over to this side of the equation, collecting all the factors of G11, and then dividing through. Now, rearranging equation 2, I obtain the following. Again, this might look like a rather strange way of writing equation 2. To get this, I multiplied top and bottom this second term here by G1n, and then collected the terms on the left-hand side. And then finally, I divided through by this term G1n minus 1 of z. So let's call this equation 3 and this equation 4. In fact, this is now all we need to form a continued fraction representation for our terminal Green's function G11. In particular, if I choose n equals 2 in equation 4, then I'll obtain G12 over G11, and that is precisely the object downstairs here in equation 3. Substituting that in equation 3, I obtain the following. I can write G11 as 1 over z minus epsilon 1 minus square modulus of T1 over z minus epsilon 2 minus, and then I have a new factor to deal with. However, this new factor is simply equation 4 with n equals 3, and so I can substitute it in again. And you can see that this will recursively generate the Green's function for G11. The Green's function is therefore given as a so-called continued fraction expansion, and the parameters of our continued fraction are entirely regular and predictable. The Green's function reads 1 over z minus epsilon 1 minus T1 squared over z minus epsilon 2 minus T2 squared over z minus epsilon 3 minus T3 squared, and so on. And for a semi-infinite chain, this just continues forever. And this is the exact representation of the boundary Green's function. Of course, with arbitrary t's and epsilons, we're never going to be able to write down a simple expression for this because it contains an infinite amount of information. However, a simple limit of this is where we set all of the epsilons equal and all of the t's equal, and then we can find a closed form analytic expression for G11. In this special limit of the homogeneous chain, we can write G11 as 1 over z minus epsilon minus t squared over z minus epsilon minus t squared, and so on. Indeed, if this sequence carries on forever, if we have a semi-infinite homogeneous one-dimensional chain, then we can recognize a self-similarity property to this continued fraction, and I can write that G11 of z is equal to 1 minus z minus epsilon minus t squared of G11 of z back again. This then gives us a quadratic equation in G11 of z, which we can solve to find the Green's function. This gives us that t times G11 of z is equal to z minus epsilon over 2t minus I times the square root of 1 minus z minus epsilon over 2t squared. Here I'm choosing specifically the negative root because I want the associated local spectral function, A1 of omega, to be positive definite. Since a1 of omega is defined as minus 1 upon pi of the imaginary part of this Green's function, I want to choose the negative sign here so that I get a positive spectral function. I also see that this gives me a semicircular density of states within a band of half width 2t, centered on omega equals epsilon. In the lecture on topological quantum matter, we considered the SSH chain. This is another special limit of the generalized model that I've written down here, in which we have alternating hoppings T1, T2, T1, T2, T1, T2, and so on, and all of the epsilons are set to 0. I'll again leave that as an exercise for you to find the boundary Green's function of that problem using this generalized continued fraction expansion and recognizing a self-similarity property. In the end, this will simply boil down to solving a quadratic equation for G11 of Z, but it'll be a different one from the one that we found here. And for the aficionados, it's a nice exercise to show that for T1 is not equal to T2, we have a band insulator, and when T1 is less than T2 in particular, we have an isolated pole living at 0 energy, which corresponds to the boundary localized topological state. So having now already looked at a few explicit examples of using equations of motion for quadratic Hamiltonians, let me now say a few more words about the generalized form of these equations of motion for a generalized quadratic Hamiltonian, which takes this form. And as usual, Tij has to be equal to Tji star for the hermiticity of this Hamiltonian. As usual, we'll denote the Green's functions of the system gxy of Z, and this means the correlation function involving the operators cx and cy dagger. Working through the usual steps, it's then easy to show that the equation of motion for gxy follows as z times gxy is equal to delta xy plus the sum over all sites in the system I of tiy times the Green's function gxi. In general, this is rather complicated because it relates a single Green's function on the left to all the other Green's functions in the system on the right-hand side. How do we deal with this in practice? Well, one way to make progress is to exploit matrix algebra. Let us define the matrix T to be the matrix of these coefficients in the Hamiltonian. This is a matrix we've encountered before, and the matrix G simply as the matrix of Green's functions. With a little bit of scratching of the head, you can probably convince yourself of the following matrix equation that corresponds to this scalar equation. We simply have that Z times the matrix G is equal to the identity matrix plus the matrix product of G times T. We can then solve this matrix equation to find the matrix G in terms of the matrix inverse of Z times the identity minus T. And of course, this is the expression that we derived via alternative means in the previous lecture. So I won't say much more about this form now, other than to say that one can derive it from equations of motion, and indeed this is a very useful expression. Again, to emphasize, the important thing here is that we can find the matrix of Green's functions without diagonalizing the Hamiltonian. The final topic of this lecture will be the study of defects and electronic scattering. So first of all, let's consider some system which I'll refer to as the clean or unperturbed system. I'll denote the clean system by H0. Later on, we're going to add defects to this system. Here I'm writing the same Hamiltonian in two different representations. First, we have a term which is basically in real space. So these are the actual physical orbitals in the system. And then I have an alternative representation, which is the diagonal representation. If the real space system is one that is periodic and translationally invariant on the lattice, then that would imply that the diagonal representation is actually momentum space. However, we needn't rely on that. Let's just say here that this representation is an arbitrary diagonal representation. The two representations are connected through this equation, which tells us the canonical transformation between the real space orbitals Cx and the diagonal representation orbitals Ck, and that is done through these complex parameters U, xk, which are elements of a unitary matrix. In the following, I'll make use of the existence of this expression, but we won't actually require explicitly these parameters u, x, k. Next, we'll consider the perturbed system with a potential scattering defect. This defect will be some local potential sitting somewhere in real space, which causes the electrons of the clean system to be scattered. We'll write that the full Hamiltonian of our perturbed system will be our clean system, H0, plus the defect, and the defect will be parameterized by this coupling constant V times the number operator for the zero orbital in real space, C0 dagger C0. I'm just choosing the zero orbital here as a reference for our potential scattering. It could be anywhere in the system. This is just a choice of the origin of our coordinate system. I can also express this perturbation in the k basis using this expansion. And then I find that I can write the full Hamiltonian H in terms of the clean piece, H0, plus this correction. This correction involves a potential scattering. We see that explicitly now from k primed to k, parameterized by this scattering strength V kk primed. That's just related to the bare potential V on site 0 and these expansion parameters in the following way. So, we'd like to know the Green's functions of our system in the presence of the defect in terms of the Green's functions of our clean or unperturbed system. Here, one can apply perturbation theory to understand the physics of this problem. However, Green's functions also allow you to find the exact solution, and so that's what we're going to do in the following. First of all, let's have a look at the Green's functions of the clean or unperturbed system. I will denote these Green's functions with a superscript 0 to indicate that it's of the clean system. The Green's functions are calculated with respect to H0. We can look at the Green's functions in k-space. G0 kk primed is equal to delta kk primed over z minus epsilon k. Or, using this transformation of operators, we can look at the Green's functions in real space, gxy0, which is then the weighted sum of Green's functions in k-space. How is the dynamics of the system changed by introducing this additional perturbation? Of course, we can introduce the perturbation and then re-diagonalize the system to find our new diagonal basis and then express the Green's functions in that way. However, we don't wish to do that. We wish to utilize the information that we already know, which is the diagonal representation of the clean system. We can now write down the Green's functions for the perturbed system using the equations of motion, and I'll do that first here in k-space. This is for the full system, and therefore I don't have any superscript zeros here. I write that z times g kk primed is equal to delta of kk primed plus this new correlation function, which involves an operator formed from the commutator of the full Hamiltonian with ck primed dagger. Notice that these Green's functions will not be diagonal in k and k primed, as they were for the clean system, because in the presence of the perturbation, the k basis is actually not the diagonal representation of the full system. To make progress, we need to evaluate this commutator, and when we do that, we obtain the following expression. In particular, note that now we have an additional sum over a variable I'm calling k1 here. The ingoing state k primed gets scattered to a new state k1. I can now write this in terms of our Green's functions g kk primed, as well as the new Green's function here g k k1. Taking this term onto the left-hand side and then dividing through by z minus epsilon k primed, we obtain the following for our Green's function g kk primed. You can see that this is not yet solved because we still have a sum over Green's functions on the right-hand side. On the left-hand side, we have a Green's function for orbitals k and k primed. On the right-hand side, we have a Green's function for orbitals k and k1. So this actually implies that we can find a self-consistent solution to this equation. This is obtained by simply inserting this expression for g kk primed back in on the right-hand side here. That gives me an equation like the following. Here we can actually break this up into the two terms, and that's helped by the fact that the first term is proportional to this Kronecker delta. That gives us the following terms. We still have the same diagonal piece at the beginning, but now we get this new factor proportional to v kk primed, and then we have a double sum now over k1 and k2. This final term is of course the problematical one, and it's again proportional to a momentum space Green's function, this time from k to k2. Now we can play the same game and simply insert this original expression back in for g kk2. When we do that, and then we collect up the terms, we obtain the following. So we see that we get a proliferation of more and more of these products as we substitute our equation back into itself repeatedly. This series seems to get more and more complicated. However, we can spot a pattern emerging, and we can actually collect together the terms, and then in the end resum an infinite series. To do this, we notice that the coefficients v, a, b are actually equal to v times these expansion coefficients. Furthermore, the local Green's function at the zero orbital of the clean system is simply given by this expression. This means that this object can be simply related to the local Green's function of the clean system at the zero orbital, and it is exactly this object that we see reappearing time and time again in this series. This is the object appearing in here, for example. Here we have 1 over z minus epsilon k1, and then we're summing over k1 times these coefficients. Notice that the factor 1 over z minus epsilon k primed and the factor 1 over z minus epsilon k are constants in this sum over k1. One final simplification is that we can reabsorb these coefficients u0k star and u0k primed times one of the factors of v here as the definition of v kk primed. By using this substitution and carefully analysing all of the terms, we can achieve this factorisation. We see that as we substitute the expression back into itself multiple times, we simply generate more of these factors. Each of these factors involves the bare coupling strength v and the local Green's function of the zero site in the clean system. The object in square brackets here can be understood as a geometric series, and we can do the infinite summation of that series. The result in square brackets is therefore 1 over 1 minus v g0. And the final result tells us that the Green's function g kk primed can be written simply in terms of the Green's functions for the clean system without the perturbation. Here I'm recognising this first factor as g kk primed 0. This is the Green's function in k-space for our clean system, which is of course proportional to the Kronecker delta kk primed. I'm also recognising that 1 over z minus epsilon k is the factor g kk 0, whereas 1 over z minus epsilon k primed is the Green's function of the clean system g0 k primed k primed. In the clean system, we have a situation where there is no electronic propagation between different k orbitals. That's kind of by definition, in a sense, because the k basis is the diagonal representation of the clean system. But when we add the perturbation, which is the potential scattering, vkk primed, we see that now we can get electronic propagation from orbital k to k primed. It's equal to the free propagator plus this term. This is called the T-matrix equation, and this object in the square brackets here is referred to as the T-matrix. So we've managed to derive here the famous T-matrix equation, which tells us about electronic scattering in a system due to a perturbation. The information about the scattering is contained in the T-matrix, which can basically be understood as the scattering amplitude at a given energy z from orbital k to orbital k primed. The so-called Born approximation corresponds to the weak scattering limit, in which we can write that v g00 is much less than 1, and then the T-matrix becomes approximately simply this scattering amplitude v kk primed. Finally, let's consider the T-matrix equation in real space. We can very simply obtain that by taking the previous expression for the T-matrix equation in momentum space, we'd had an equation for g kk primed, and simply multiplying it by these coefficients and summing over all k and k primed. That will then give us the Green's function in real space gxy in the presence of the perturbation. When we do that, and converting everything into real space Green's functions, we obtain the following T-matrix equation. We see that the Green's function between sites x and y in real space for the perturbed system can be related to the free propagator between x and y for the clean system, plus this correction, and this correction involves the free propagator from x to the 0 site, where the perturbation acts, times the T-matrix, times the propagator from the 0 site back to the y site. The real space T-matrix T of z follows immediately by applying this transformation to our T-matrix equation in momentum space. We find that T of z is simply v over 1 minus v g0. Thereby, we can relate all of the Green's functions in our perturbed system to the Green's functions of our system without the perturbation. We don't have to completely rediagonalize our system when we add the perturbation. We can simply relate the new Green's functions to the old ones. And notice that here this is the exact result for the T-matrix. We didn't actually have to do perturbation theory here, which would only be approximate in orders of v. We basically did the infinite order resummation of that geometric series to obtain this exact result. The final topic that I want to cover in today's lecture is the scattering from so-called quantum impurities. We'll again write down an unperturbed Hamiltonian H0, which consists in real space of some quadratic type binding model that I'm writing down here. And then, as before, we can express this in the diagonal k-space representation, where we have a canonical transformation between our real space operators Cx and our k-space operators Ck. We now imagine to this system, which I've sketched here in black, adding an impurity, which is an extra site into the system. This is this red orbital, and it couples somewhere locally in real space. The perturbation in this case is therefore not simply a local potential, but an extra site in the system, and I'm labelling that here D. And we have associated creation and annihilation operators for this new site D dagger and D. This new site is the so-called quantum impurity. Here we see that the full Hamiltonian of the perturbed system is H0 plus the tunneling V between a chosen site, which again I'll call C0, and this additional site D. I'm also giving the quantum impurity its own level energy epsilon. So this is a bit different from the previous example because our impurity D is not actually a part of the Hilbert space of H0. We'll start, as before, with the Green's function of the clean system, and in particular, we'll focus on the local site C0. The Green's function G00 of the clean system, again denoted by these superscript zeros, is therefore this object. We can find an expression for it in closed form by using the diagonal representation. Let's have a look now at the Green's function of the perturbed system. In particular, let's have a look at the Green's function of the impurity itself. I'll denote that GDD, and that basically means the correlation function of D with D dagger, in which the impurity D is coupled to the conduction electron C. We can now use equations of motion to find the impurity Green's function in the coupled system. Evaluating the commutator with the full Hamiltonian, we find a term epsilon D dagger and a term V C0 dagger. We can also express the C0 dagger operator in terms of the diagonal k-space representation as V times the sum over k of the expansion coefficient U0k star times the k-space operator Ck dagger. Plugging all of that in, we can now rearrange for the Green's function in the impurity. This allows us to write GDD back in terms of GDD, but then we also have this other correlation function, which is like a cross term involving the D operator of the impurity and the Ck dagger operator of the conduction electrons. So we apply the same strategy as before, and simply apply the equations of motion again, but now to this new correlator. Given that D and Ck definitely belong to different Hilbert spaces, they certainly anti-commute, and therefore this first term is equal to 0. The second term is this correlation function involving a new operator formed from the commutator of the Hamiltonian, the full Hamiltonian, now with ck dagger. Utilizing the k-space representation of our perturbation Hamiltonian, we can easily calculate this commutator, and we obtain epsilon k ck dagger plus the perturbation term v times the expansion coefficient u0k times the creation operator d dagger for the impurity. This is nice because it allows us to relate the correlator d ck dagger back to our impurity correlator gdd. Specifically, we can write that z minus epsilon k times the correlator d ck dagger is equal to v times the coefficient u0k times the impurity Green's function gdd. We can now substitute this back into our original equation of motion for the impurity Green's function to eliminate this unwanted correlator. We then obtain the following expression for gdd. Notice in particular here that we see a quantity appearing that we calculated previously. This object is nothing other than the local Green's function of the C electrons at the impurity position in the clean system. And now we can collect all of the factors of gdd on one side and find our final expression. We can write that gdd is equal to 1 over z minus epsilon minus a hybridization function delta, which here I've defined as being v squared times the local Green's function of the C electrons at the impurity position in the clean system without the impurity. The philosophy of this calculation is rather similar to that of the T-matrix equation that we looked at previously. We find the Green's functions for the coupled system in terms of the Green's functions for the uncoupled system. Here we have a Green's function for the impurity, which can be related to this hybridization function, and this only involves properties of the environment, that's the C electrons in this case, in the absence of the impurity. The Green's function for the impurity takes the form of the so-called Dyson equation. I can write the inverse Green's function, gdd inverse, in terms of gdd inverse for the system without the coupling to the environment, and then minus the hybridization function. gdd 0 is simply 1 over z minus epsilon for a single d site uncoupled to the rest of the system, whereas the hybridization function delta is simply v squared times g00 for the uncoupled system. To understand what this impurity Green's function looks like, let's consider the so-called wide flat band limit of the conduction electron system. Let's suppose that we have a density of states rho naught of omega for our C electrons, which is defined as usual as minus 1 upon pi of the imaginary part of this Green's function. In this particular case, let's suppose that this density of states is flat. It takes a constant, rho naught, inside a band of width d. This Heaviside step function here gives us 0 when omega is outside of d, and it's constant and equal to 1 when omega is less than d. So we simply have conduction electrons in a band of half width d, and everywhere inside the band we have a constant density of states. For this density of states, what is the corresponding hybridization function delta of z? Well, this of course depends on the local Green's function, and here we're just writing down the imaginary part of that Green's function. So knowing the imaginary part, how can we extract the full Green's function? Well, we can write the full Green's function, g00 of z, in terms of its real part, minus I pi times the density of states, following from this definition. As explained previously, because Green's functions are analytic functions of the complex variable z, it means that the real and imaginary parts are related through the so-called Kramers-Kronig transformation. Therefore, if I know the imaginary part, I can determine the real part. Specifically, I can write the real part of g00 is minus the integral d omega primed over all omega primed of the density of states rho 0 of omega primed over omega primed minus omega. And here it's understood that I'm taking the principal value integral. That just means that we're avoiding the poles downstairs here. Now, if we insert the specific flat density of states inside our band of half-width d, then this integral simplifies. We simply have minus rho naught of the integral inside the band from minus d to plus d of 1 over omega primed minus omega. This integral simply evaluates to rho naught times log of d minus omega over d plus omega. In particular, the real part of this Green's function goes to 0 as d goes to infinity. So when considering the wide flat band limit, we only need to consider the imaginary part. We can then set the hybridization function delta of z simply to minus I pi v squared times rho naught inside the band, but given that the band is infinitely wide, we can just write it like this. It's conventional to absorb the factors pi v squared rho naught into the definition of a constant gamma, which, as we'll see, sets the level width of the impurity Green's function. So let's now substitute this hybridization function for conduction electrons in the wide flat band limit back into our Dyson equation for the impurity Green's function. We can now write the impurity Green's function as 1 over z minus epsilon plus I gamma. We can then write the corresponding spectral function for the impurity, which is minus 1 upon pi of the imaginary part of this Green's function, as we take the complex variable z to the real axis. We can then write that in the following way, which is the familiar form of a Lorentzian. The Lorentzian is centered on omega equals epsilon, and it's of width gamma. The impurity spectral function, therefore, looks something like this. In particular, we see that the isolated impurity, not coupled to the conduction electrons, would simply be a delta peak centered on omega equals epsilon. However, because of the coupling to our bath of conduction electrons, this delta peak gets broadened into this Lorentzian, and the half-width at half maximum of this Lorentzian is precisely this hybridization gamma. This is why the hybridization is sometimes known as the level width. This can also be understood as the lifetime broadening of the spectral line, as discussed in the previous lectures. An isolated impurity has an infinitely long lifetime, but when the impurity gets coupled to the conduction electrons, there's a finite probability that the electron escapes into the conduction electron bath, and this gives the spectral line some width, and that's precisely this hybridization. Previously, we considered this line broadening to be a phenomenological factor, but here we see explicitly through an actual calculation that when we couple a local level to a continuum, then we see exactly this line broadening effect. Finally, let's consider again the famous fluctuation dissipation theorem as applied to this impurity problem. Now that we've worked out the spectral function in the real frequency domain, AD of omega, we can now determine the lesser Green's function, G lesser d of omega. Here, the f of omega is the usual Fermi function. Since G lesser d of t is defined as I times the thermal expectation value of d dagger evaluated at time 0 and d evaluated at time t, we can then work out the expectation value of the occupation of our impurity level. This is the expectation value of nd, which is simply minus I times the 0 time value of our lesser Green's function. We can relate this to our lesser Green's function in frequency space by taking the inverse Fourier transform, and we get minus I upon 2 pi of the integral over all omega of G lesser of omega. This gives us our general result that the expectation value of the occupation of a level is equal to the integral d omega of the spectral function for that level times the Fermi function. This is good because we've just calculated the spectral function of our level over here. It's simply this Lorentzian. As we change the level energy epsilon on our impurity, this Lorentzian moves around. In particular, when epsilon is very positive, there's not much of the tail of this Lorentzian that overlaps at negative energies, and therefore at low temperatures we don't expect there to be a very large occupation of the level. On the other hand, when epsilon is negative, we see the peak arises at negative omega, and then we'd expect the integral to pick up a large contribution, and we'd expect the occupation of the impurity level to be quite large. Of course, we have all of the equations here to make this quantitative. In particular, if we look in the low temperature limit as t goes to 0, we can evaluate this integral analytically because the Fermi function simply becomes the step function. We find that the expectation value of the impurity occupation is 1/2 minus the arctan of epsilon over gamma over pi, and I've sketched it here. I'm plotting actually on the x-axis epsilon over gamma, which we see here are the natural units. When epsilon over gamma is much less than 0, then we see that the impurity is singly occupied. Its occupation tends towards 1. When epsilon over gamma is 0, the impurity is exactly half filled, and for epsilon over gamma much greater than 1, the impurity empties out. The impurity electrons escape into the conduction electron bath, and we see Nd tends to 0. The role of the hybridization gamma here is to broaden the crossover from the single occupancy to the empty state of the impurity as a function of epsilon. As we make gamma smaller, the crossover becomes sharper. So, in this lecture, I've introduced the equations of motion technique for Green's functions, and we've been through a lot of instructive examples. I've talked also about the T-matrix equation for scattering due to a local potential, and we've seen some examples of quantum impurity physics, in which we have a local level hybridizing with a continuum of conduction electrons. We see that equations of motion are very useful for these kinds of systems and actually make quite light work of otherwise quite difficult problems. In the next lecture, which will be the last lecture on Green's functions, we will see the layman representation of the Green's function, which will allow us to tackle more naturally systems of interacting fermions.